moderators, and all the researchers in this session. First of all, I would like to introduce myself. My name is Kenny. I'm a PhD student under University Malaysia Police. My work emphasizes on fingerprinting localizations and deep learning applications. Today, I would like to thank the opportunity given by INCAP 2021 committees to allow me to share one of my recent work with the title of Methods for RSSI Heat Map Estimation using Radio Basis Functions for Fingerprint Localization. Let's start with some introductions of localization. Localization refers to the process to obtain location information with respect to a set of reference position within a predefined space. There are many kinds of localization application in our daily life. For instance, there is GPS system in our smartphone. However, do you know that GPS has their own limitation? Let me give you an example. When we order foods from food delivery applications, do you notice that sometimes the application requests us to pin our exact locations that we are currently in to allow the food to be sent to us? Why does it so? This is because the GPS system are limited for outdoor applications. It is not designed to locate people or objects within the indoor environment. However, our human characteristics that has been shown in some research that stated that 70% of our human lifetime will be spent in indoor environment. For instance, we are attending this conference in an indoor environment such as our house, office, or other indoor environment. Therefore, it shows the importance of indoor localizations in our human daily life. This work has been carried out in one of the university laboratories with a size of 24 meters times 8 meter range. We have used 2.45 GHz active RFID systems placed at different locations to collect the RSSI between the transmitter and the receiver. Given that the separation distance of 1 meter for each fingerprint locations, there will be 225 fingerprint locations that requires us to collect the RSSI value. However, due to the obstacles available in the environment, we can only collect 197 fingerprint locations. This results in incomplete radio mappings that could possibly degrade the performance of the localization. In this experiment, the true value of RSSI at every single fingerprint locations can be determined by averaging the collected RSSI collected within the given window period. Based on the plot, you can see that there are some missing plots at certain locations, and this is because of the laboratory hardware that placed within the environment. There are also possible of other signal propagation factors that results in total drop packets as shown in some of the locations on the slide. Therefore, in this case, we propose RBF interpolations method to generate the complete radio maps for the fingerprinting localization. In order to evaluate the feasibility of RBF interpolations method proposed in this work, we have considered two different scenarios that has the reduced amount of fingerprint locations, which is represents by 42% of the total numbers of fingerprint locations and 76% 70% of the total number fingerprint locations as shown on the slide. With the considerations of probability of occurrence (POO) at single RSSI at single fingerprint locations, we convert the RSSI value in terms of probabilistics and stack all the probabilistics radio maps to generate a RBF interpolations to complete the radio mappings. There are one as shown on the slides, the GIF versions for every single probabilistic value for the RSSI. As you can see the moving GIF version on the slide. We use the highest probability at each of the fingerprint locations to determine the RSSI value that represents the fingerprint locations. Based on the radio maps or in the slides, the RBF not just able to predict the RSSI value at every single fingerprint location, but also covers all the fingerprint locations that has been blocked by the furnitures and also hardware as experimental hardware presence in the environment. The performance of each RBF interpolated radio mappings is compared to the true value of the RSSI radio maps. We compare every single available fingerprint location without considering the missing plots. Okay, and we can obtain the absolute error by dividing the numbers of fingerprints to produce the radio maps. There are two different scenarios in this work. For 42% of reference fingerprint locations, the mean error varies between 3.244 dBms to 3.339 dBms for three different types of RBF interpolated methods. Meanwhile, the 76% of reference positions, the mean errors varies between 2.2008 dBms to 2.056 dBm. It is noticeable that using higher amount of reference fingerprint location in RBF interpolation methods would generate lower errors in the radio mapping estimations. It is also observed that when the reference fingerprint location reduced more than half of the original readable fingerprints, the mean error increased significantly. One of the possible reasons for this outcome is due to the unique representation of RSSI may not able to reconstruct if the reference position are reduced more than 50%. As a summary for this work have shown the feasibility of RBF interpolation method to reduce the time and effort to build out the radio maps for fingerprint localization, as we are not required to evaluate every single fingerprint locations to generate the radio maps. Based on the work, inverse multi-quadric RBF interpolated radio mappings has the best mean error of 2.008 dBms for the 225 fingerprint locations. However, this work would suggest that the best performance of any interpolation method are subjected to the laboratory conditions and structures. Although there are some errors are observed in the RBF interpolated radio maps, the labor and time requirement are reduced to generate the radio maps. The trade-off between time, labor effort and errors are necessary to be done in this case. That is all for my presentation today. Thank you very much for lending your ears. If there's any questions, you can contact me through the emails as shown on the slide. Once again,